Hey guys, today we're going to learn about differentiation. Our topics today would be to cover the definition of differentiation, there's a few, and the uses. Why is this chapter, this topic important in your syllabus, in what you guys are studying? And how does this help us? So the definition, I've listed three. The first one would be the rate of change of a function. That means how fast a function is changing. I will talk about this more in a later video. The next definition would be the process of finding the derivative. After you differentiate something, you will get the derivative. The third definition would be the process of finding the gradient function. So after you differentiate a function, you will either get, you can call that thing after differentiation, a derivative or a gradient function. Either one is fine. But I'll start explaining why it's called the gradient function in this video first. Now, let's look at the gradient of a linear function. A linear function is just a function of a straight line. So, for example, this is my function. Fx equals to negative 3 over 2x plus 3. And if I were to take this function and I were to plot a graph with it, this is what it'll look like. I will have two intersects, P and Q. So those two parts are the intersecting lines. P is intersecting the Fx line, the Fx axis. And then my Q coordinate is the intersection between my line and the x-axis. Okay, so we know the gradient formula. It's y, the second y minus the first y, all over the second x minus the first x. Okay, y2 minus y1 over x2 minus x1. Now let's call these points some names. Yeah, I'm gonna call point P the second coordinate. So 0 is gonna be x2, and then 3 is going to be y2, where Q is gonna be the first coordinate then. So Q is going to be, the 2 is going to be x1, and then the 0 is gonna be y1. And I'll just plug these coordinates into that formula. As you can see, the y2 is now at a 3, and the y1 is going to be a 0 from Q. And then the x2 is going to be a 0 from P. The x1 is going to be a 2 from Q. I'm not going to talk about how we're deriving this formula. I'm just going to use it, and I'm going to show you why this is important. Okay, so now I have the gradient of this function. For those of you who understand gradient, you should know that we don't even need to use the formula to get the gradient. We can actually take it from here. Whatever's attached to that x, that's going to be the gradient of any linear function. Okay, now, what if we're talking about the gradient of a quadratic function? Let's say this is my quadratic function. A quadratic function, that means the highest power of x would be x squared. And then this would be the graph that comes with it. Right, so in this graph, I've highlighted 3 points that I want to make note of. Point A, which is that negative 1, 0, which is the first root of this function. And then point B, which is the fx intercept. And then point C, which is the second root of this function. So I have these 3 points. Now, notice that for this function, it's a little different from the function that we did previously. The previous function was a linear function. So all the points in that function are all following the same gradient. They're all falling down. Let's go back and see. They're all falling down. So if I were to take point P or point Q or any other points along this line, it's going to follow the same gradient. But now that I'm doing a quadratic function, notice that I have points going down, and I also have points going back up. Now, for us to find, we cannot find a single gradient to represent the entire graph. This is why we need a gradient function. We need a gradient function because the gradient function will give us the gradient of every point as long as we substitute the right coordinates into it. So these are our notes. Like for example, this one, yeah, it has its own gradient, and this point, it has its own gradient. So our notes would be, every point has a different gradient. As you can see, there's a straight line going down here, but there's another straight line going up at this point. Second, we cannot use a single gradient to represent the entire function because we know that the gradient is changing over time. The gradient is changing as we're moving from one point to another point. Third thing, we need a gradient function that can change according to the position. Okay, a function that tells us the gradient of this original function. Now, I'm going to take the same things again, but this time, I'm not going to show you how to get the gradient function just yet. I'm not going to show how to differentiate just yet. I'm just going to give it to you, and I'm going to show you how it's being used. Let's say this is the gradient function of this equation. This fx equals to x squared minus 2x minus 3. The gradient function for that would be this, fx equals to 2x minus 2. Now, at point 0, 3, which is that point B, that fx intercept, if I were to plug in my formula, the gradient function, I know that these x spaces, I just have to include my x from this point, so that would be 0 and 0. And then I find that the gradient is actually negative 2. So that means at point 0, 3, where the slope is going down, the gradient is negative 2, which makes sense because we know that whenever linear functions go down, it's going to be a negative gradient. Now let's look at point C, 3, 0. Yeah, I'm just going to show you that point. Yeah, this is a negative gradient because it's sliding down. Now, if we look at point 3, 0, which is that point C, this is the same gradient function that I took from up here, the one that's highlighted in red. And I'm going to substitute my x values. So that's going to be f3 equals to 2 times 3 minus 2. And I find that my gradient for that specific point is 4. Okay, this specific point at point C, the gradient is positive 4, which makes sense because this line is heading up. Whenever our lines are heading up, it's going to be a positive gradient. So basically, this is the understanding behind why we need to find a derivative, or if you want to call it the gradient function, or why we have to differentiate. Because this helps us understand the graph more, and it helps us easily see at every point what their gradient is. And that's going to help us in any future math that we will apply. Okay, so again, let me repeat just to summarize. This would be the function. This would be the gradient function, which tells us at every point what their gradient is. This is why we learn differentiation. Okay, thanks for watching. Remember to like, share, and subscribe.